Okay, picture this. You grab a completely ordinary, everyday object, like a potato, and you drop it onto your kitchen scale. You read the number, let's say it's 200 grams, and you just naturally assume you're measuring the physical stuff sitting right there. Makes sense, right? Well, what if I told you that simple little number on the scale is actually a massive illusion? It's hiding one of the most mind-bending secrets of our universe. Today, we're going to completely unravel how we understand reality, literally starting from the absolute tiniest building blocks of matter and zooming all the way out to the very fabric of space-time itself. Welcome to this explainer. I am so incredibly excited to guide you through this journey. We are going to deconstruct reality as we know it, moving from the strict microscopic rules of atomic physics right up into the fundamental cosmic nature of mass and energy. I promise you, by the end of this, you will literally never look at a potato or honestly anything else the exact same way again.
So here is our roadmap for today. We'll kick things off with the quantum blueprint, then move into the rules of atomic construction. After that, we'll hit the potato mass paradox, dive into energy, momentum, and gravity, and wrap up with the Higgs field origin.
Let's jump right in. Section 1. The quantum blueprint, the foundation of matter.
Okay, let's dive into this. To build an atom, you have to arrange electrons around a central nucleus, but they can't just float around wherever they feel like it. Their entire existence is strictly governed by 4 quantum numbers. You can kind of think of these as the ultimate microscopic coordinate system. The principal number, n, dictates the energy level and the overall size. Then you have the azimuthal number, L, which gives us the actual shape of the subshell, so whether it's spherical like an s orbital or shaped more like a dumbbell for a p orbital. Next up, the magnetic number, m, tells us how it's oriented in 3D space. And finally, the spin number, ms, dictates the electron's intrinsic rotation, which is strictly limited to either up or down.
Now, checking out this table, it brilliantly illustrates how these seemingly abstract numbers actually translate into incredibly rigid physical limits. The underlying math directly caps exactly how much each subshell can hold. Your S subshell maxes out at exactly 2 electrons, the P subshell takes 6, D takes 10, and so on. And remember, this isn't just a gentle suggestion. It's a strict mathematical law dictating the basic architecture of literally every single atom in the universe.
Let's move on and see how this actually builds. Section 2, Rules of Atomic Construction, Building the Elements. So, building an atom is essentially like following a highly specific cosmic recipe. First up is the Aufbau principle, which basically tells us that electrons are, well, a little lazy. They are always going to fill the lowest available energy states first. Next is the Pauli exclusion principle, which is absolutely crucial. It's arguably the most important rule for why solid matter even exists. It states that no 2 identical fermions, like our electrons, can ever share the exact same set of 4 quantum numbers. Without Pauli's rule, all the electrons would just collapse into the lowest possible energy state together, and chemistry as we know it simply wouldn't happen. Finally, we have Hund's rule, which says that electrons actually prefer to spread out within a subshell with parallel spins before they're forced to pair up, just to minimize the energetic repulsion between them.
Now, what's really interesting about this is how physicists quickly summarize all this complex quantum architecture. They use a really standard, simple notation. Take helium, for example. It has 2 electrons tightly packed into that lowest energy spherical orbital, so we just write it as 1s squared. The 1 is that principal energy level, the s is the spherical shape, and that little superscript 2 represents the number of electrons. It is a wonderfully simple shorthand for a seriously complex quantum reality.
All right, Section 3, the potato mass paradox, the illusion of everyday matter.
Okay, so we've just laid out the microscopic rules governing individual atoms. But if we scale that whole system up, grab trillions of those atoms, and build our everyday potato, things start getting pretty wild. If you take that potato and add up the individual rest masses of every single fundamental particle inside it, so we're talking every quark inside every proton and neutron plus every single electron, you would naturally expect that math to perfectly equal the weight on the scale. But it doesn't. In fact, it's not even close. The rest mass of all those foundational particles only accounts for about 1% of the potato's actual measurable mass. Crazy, right?
So where on Earth is the other 99%? Well, the overwhelming majority of the mass of that potato isn't physical stuff at all. It is entirely potential energy. Specifically, it's the massive potential energy of the color-charged quarks and gluons fiercely interacting within the incredibly intense strong force field inside the protons and neutrons. The sheer amount of energy required to bind those particles together is just immense.
And this brings us right back to Einstein's legendary equation.
E equals mc squared is not just a neat math trick you learn in high school. It is a literal, fundamental description of reality. All energy has inertia, and all energy exerts a gravitational pull. So the binding energy of the strong force holding the inside of that potato together literally translates into the physical mass you are measuring on your kitchen scale. When you weigh an object, you are largely just weighing the confined energy of quantum fields.
Moving right along. Section 4. Energy, momentum, and gravity. Redefining space-time.
To really wrap our heads around this mass-energy equivalence, we actually have to redefine how we think about space-time itself. And to do that, I want to pose another question to you, straight from the depths of theoretical physics. Is energy a component of momentum? I know, from a simple dimensionality standpoint, it sounds a bit crazy. But relativity tells us that the universe absolutely does not separate space and time the way our human brains do.
So the crucial point here is that in special relativity, we live in a four-dimensional universe. To locate any event, you need three spatial dimensions, your x, y, and z, plus one dimension of time. We call this the four position. Now, if we translate this whole concept over to frequency space using mathematical tools like Fourier transforms, we end up with what's called the four-momentum vector. And just as time is the fourth component of your physical position, energy is fundamentally the time component of momentum. They aren't separate, isolated concepts at all. They're just different faces of the exact same physical reality, entirely depending on your frame of reference.
And you know what? This completely rewrites Isaac Newton's laws. In general relativity, mass alone is not the source of gravity. Because mass is energy, and energy is literally a part of momentum, the true source of gravity is actually something called the stress-energy tensor. Now, I know that term sounds a bit intimidating, but it basically just describes the flux, or the current, of energy and momentum flowing through space-time. This means that not only does energy density create gravity, but things like extreme pressure and shear stress do as well. The energy bundled up inside our ordinary little potato is literally warping the fabric of the cosmos around it.
Which brings us to our final piece of the puzzle. Section 5. The Higgs field origin, where rest mass begins. Okay, so we've solved the big mystery of the 99% of the potato's mass. It's all strong force energy. But wait, where do those original quarks and electrons actually get their base 1% of rest mass to begin with? Well, if you were a physicist hunting for the source of this particle rest mass, you know your source field had to meet some incredibly specific conditions. First, it absolutely must permeate all space because an isolated electron still has mass no matter where it is in the universe. Second, it has to take the exact same constant value everywhere. And third, it must have zero spin. If it had spin, it would give empty space a specific direction, completely breaking the uniform isotropy of the void. And this brilliantly illustrates the final answer, the Higgs field. Just fractions of a tiny second after the Big Bang, as the entire universe began to cool, the Higgs field settled into a non-zero ground state. It basically froze into place, permeating absolutely everything. So now when elementary particles like quarks and electrons travel through space, they're forced to interact with this constant background field. This interaction acts as a form of potential energy, and as we've learned today, potential energy is mass. The Higgs mechanism is the ultimate true origin of that foundational 1% of matter.
So, we started today with a simple potato, and we've journeyed through the rigid quantum rules of the Pauli exclusion principle, the massive potential energy hidden in the strong nuclear force, the space-time bending nature of the stress-energy tensor, and finally, the pervasive Higgs field. But it all comes back to this one truly profound thought. The solid world you and I interact with every single day is mostly an illusion. It is not made of hard, rigid stuff. It is fundamentally made of interacting quantum fields, binding energy, and the curvature of space-time. All mass is energy, and all energy is mass. So the next time you pick up any object, just remember the incredible cosmic forces working tirelessly behind the scenes just to give it weight. Which leaves us with one final, kind of unsettling question. If the solid world is really just an illusion of trapped energy, what does that mean for the very fabric of you and me? Thanks so much for joining this explainer. I'll catch you next time.